Hi, welcome to today's chemistry video about nanocellulose and nanofibers. This is a nice picture of a suspension of ultrasonicated nanocellulose in water. The nanofibers have typically a diameter from 1 nanometer to 1 micrometer. They have a big surface area to volume ratio, a high porosity, and high mechanical strength. The nanofibers were discovered by English physicist William Gilbert in the 16th century with the electrospinning technique. This is one method to make nanofibers, especially nanocellulose, from cellulose material, for example wood pulp, using the chemical tempo. This is the compound tempo, 2266 tetramethylpiperidinyl or enzymatic hydrolysis. This is the compound. The ring atom is the highest atomic number, is number 1. In this case, it's nitrogen. It's number 2, 3, 4, 5, 6. That's why 6, 2, 2, 6, 6. And this treatment has the advantage. It gives this pre-treatment makes it easier, and you need less energy for making the nanocellulose by mechanical disintegration. This is one of the potential applications of nanocellulose as a substrate for flexible solar cells, or for composite materials, or for the food industry, for example, as thickener. Or you can use it in medicine, for example, for wound dressing, for diapers, and for energy storage. This is another method to make nanofibers by electrospinning. This is a picture of polyvinyl alcohol in aqueous solution. The liquid droplet is applied. You apply a high voltage to a liquid droplet that stretches the droplet. The nanofibers erupt out of the cone that's called the Taylor cone. They are elongated by electrostatic repulsion down to nanometer size diameters. This is a picture of electrospun nanofibers, a scanning electron microscope image. And you can see the nanofibers have very comparable diameters. This is very good, because this means you have a controlled process. Very few of the fibers, for example, these two have a smaller diameter, but most of them are comparable in the diameter size. There's another method called TIPS, thermally induced phase separation. It has 5 steps. First step is the solution of the polymer. Second is the polymer phase separation. Third step is the gelation of the polymer. Fourth step is the extraction of the solvent from the gel. And the last step is the freezing or freeze-drying in a vacuum. For this method, important parameters are the temperature, the solvent, and the polymer concentration. This is another synthesis method, the template-assisted synthesis of 1D nanostructures. You use a template, for example, graphite. This allows you to make fibrils and tubules. So this is a production method for nanofibers from metals, semiconductors, or polymers. The advantage is you can achieve very small diameters. The disadvantage is this is not a continuous production process. This is another potential technique, the self-assembly technique. This is a movie of atomic force microscopy image of 2 amino terephthalic acid molecules on calcite. You can see on the top the nucleation, and at the bottom the growth of these nanofibers. This technique is important for the synthesis of peptide nanofibers. Important parameters are the hydrogen bond, van der Waals forces, pH, and for example ionic bonds. These are essential factors for the synthesis of these types of nanofibers. This is one of the applications of nanofibers for tissue engineering. This is a nice picture of structure of bones. Bones are composite materials of 70% bound minerals, for example, hydroxyapatite, calcium phosphate hydroxide, and 30% flexible matrix of collagen. And you can use nanofibers for scaffolds of biodegradable polymers for rebuilding of bone structures. There's another use for nanofibers, that's for optical fibers and sensors. Nanofibers are known for the high surface area to mass ratio. this allows a high sensitivity. The advantages are low costs, biocompatibility of nanofibers, flexibility and high transparency. And you can use nanofibers for humidity sensors and chemical detectors. This is a very impressive picture. This black in black is a human hair. You can see STOF, the sub-wavelength diameter optical fiber. Its diameter is smaller than the wavelengths of the light. This optical fiber is known to be very fragile and it is sensitive to dust, but it has a big potential for sensors and for quantum information processing. This is another very interesting technology which is not ready yet. That's the lithium air battery. It is at high theoretical specific energy density of up to 5,000 to 11,000 watt-hours per kilogram. And carbon nanofibers have a big potential as a cathode material because of their big surface. This battery is still in development, and if you had this battery today, you could easily make a very big electric airplanes, passenger airplanes, and that's why this is relevant. There's another scanning electron microscope image of polyaniline, PANI, nanofibers. There's synthesized from aniline. Aniline is a very important compound, organic compound for the chemical industry. The method is oxidative polymerization. And these PANI polymers are known to be conductive. They have diverse applications, for example, for sensors or memories. And the global conductive polymer market in 2022 was a $5.8 billion market. There's another application of nanofibers in sportswear. You can make textiles within a membrane of polyurethane nanofibers. It gives you water resistance and at the same time breathability. And you make use of the Sieve effect of the more than 2.5 billion pores per square centimeter. There's another picture of polyurethane PU fibers. This optical microscope image 100 times magnified. Nanofiber membranes for polyurethane via electrospinning synthesis are very important for passive radiative cooling, PRC. So these materials have a 93% infrared emissivity, and this can cause up to 10 degrees Celsius temperature drop at midday. At the same time, if you stretch this membrane, you can turn it into a heat absorber. This is another picture of polyacryl on nitrile, PAN fibers in polarized light. You can make composite materials of electrospun polyacrylonitrile nanofibers with magnetic manganese iron oxide nanoparticles or membrane catalysts. And they're efficient for the degradation of organic pollutants and with magnetic inductive heating in a big range of pH from pH 3 up to pH 10. And you have a higher degradation efficiency of 80%, more than 80% in the presence of hydrogen peroxide. This is another nanostructure, that's zinc oxide. This is an electron microscope image of zinc oxide nanoflowers. You can make a composite of zinc oxide nanofibers with cadmium sulfide nanoparticles. And you can make a photocatalyst for wastewater treatment. The cadmium sulfide improves the photocatalytic activity. And the method to make these compounds is also the electrospinning synthesis. This is a beautiful electron microscope image of zinc oxide nano snowflakes. And this is a very nice nano art. That's the surface of a nanostructured gallium arsenide. You can see the coastline, the boundary between the two phases. And you can see the formation of the nanocrystallites by the island mechanism. It's a very beautiful image. The science is interesting and the image is also very beautiful. And that was today's video about nanoflowers and nanofibers. You can check out the links in the description field, and you can check out my other videos in the nanotechnology series. Thank you for watching. Have a nice day. Bye bye.